From a young age, almost all of us have heard that opposite charges attract and like charges repel. But how do we describe charged objects and particles, and how do they exert forces on one another? Charge, like mass, is what's known as an intrinsic property of an object. It's a fundamental property to the object that we can measure. However, unlike mass, an object can either have a positive or negative charge, depending on how many protons and electrons it has, where protons are positively and electrons are negatively charged. Another property of charge is that it's quantized, or always shows up in multiples of one elementary constant. In this case, the elementary charge constant is equal to the charge of one electron or proton, which has a magnitude of around 1.61 times 10 to the negative 19 coulombs, which is an extremely tiny number. Now, there's two main types of charged objects that you'll come across in AP Physics 1, conductors and insulators. Conductors are usually metallic and are characterized by the ability for charge to move freely through and inside of them. Insulators, on the other hand, are mainly plastics, rubbers, and non-metallic objects, and the charges within insulators are generally fixed or unable to move around. While insulators can generally be charged through friction, like rubbing a balloon in your hair, charging conductors can actually be done through two main processes, namely conduction and induction. Conduction involves the direct contact of one charged conductor with another. Now, with regards to interactions between charged objects, it's important to note that charge within closed systems, like mass, is always conserved. For example, if I were to have a metal sphere of charge positive 3 coulombs and touch it to an identically shaped sphere of charge negative 1 coulombs for a long time, the charges would conduct through the spheres, with the total charge of the spheres of positive 2 coulombs remaining constant. After a short while, both spheres would have an equal charge of positive 1 coulombs on each, and the charges would reach equilibrium. Another vital distinction to make here is that charges that move are actually electrons, never protons. Using our background knowledge that opposite charges attract, we can say that the negatively charged electrons will move from the negative 1 coulomb sphere to the positive 3 coulomb sphere until both spheres reach charges of positive 1 coulombs each. The second and slightly more complicated charging method for conductors is what's known as induction. This process involves 4 simple steps, and while the end charge on objects charged through induction is very difficult to calculate quantitatively, let's see how we can actually give an object a charge opposite to the charge of another object through induction. The first step is to bring a charged object close to the object you're trying to charge. This charged object will rearrange the electrons and protons within your original object through a process known as polarization, as the charged object will attract its opposite charge and repel its like charge. The second step is to ground our original object, or connect it to Earth. What this does is it allows charges to flow freely into and out of the object from and to the Earth. Based on the charge of our charged object, electrons can be repelled out of the object or attracted into it, giving the original object a charge of opposite sign to that of our charged object. Finally, the third and fourth steps are to remove both the grounding source as well as the charged object. What we're left with is an object that has a charge that's opposite to the charge of our originally charged object that we used, and this process is known as charging by induction. Now, as we all know, like charges repel while opposite charges attract, but the magnitude of this electrostatic force is actually given by Coulomb's law, or that the force equals a constant k times the first charge times the second charge, all over the distance of separation squared. Although this force is not actually applied by a wall, hand, or string, the Coulomb force is, equation-wise, exactly the same as forces like the normal force, applied force, and tension. Used in tandem with Newton's second law, or that the net force on an object is equal to its mass times acceleration, charged objects act like any other block or ball from past units. Only now, they feel an extra Coulomb force in addition to whatever other forces are relevant. Charged objects and particles, in my opinion, are easily one of the hardest concepts to grasp in the AP Physics 1 curriculum. They're invisible to the naked eye, deal with extremely large or small numbers, and apply forces without touching anything. But for now, you can feel good that you've just learned about charge, charging methods, and Coulomb's law.